Hello everyone, welcome back to my channel. I am Syed Irfan studying Electronics and Communication Engineering in Sri Venkateswara College of Engineering, and I am pursuing Electronics and Communication in second sem. This video is for my school assignment purpose. Apart from the other videos I have been posting in this channel, this video will be different where I will be explaining Gauss divergence theorem throughout the video in slide mode. This video is different from the other videos I've been sharing. As I've mentioned, this video is for assignment purpose. To start with, Gauss divergence theorem, I will be explaining the statement, principle, and the practical applications of this theorem. So let's start the video. First, let's start with what is Gauss divergence theorem. What does this theorem state? What does Gauss divergence theorem state? It states that this theorem enables us to convert a volume of integrals into surface integrals and vice versa, which means we can convert the volume integral volumes to surface volumes as well as surface volumes to integral volumes. As you can see in the vector field, this is a vector field F and this is a Gaussian surface. This actually is a 2D divergence diagram. The actual diagram, the actual it would is in the 3D way. This diagram shows in the 2D divergence. Next slide, the statement states that the volume integral of the divergence of field A. That means there exists a field A where the volume integral is taken and it is taken over a volume of V. The surface has volume V, which is equal to the surface integral of the vector field A. That means that there's a vector field A and the volume which is taken is equal to the surface integral of this vector field A taken over closed surface bounding volume V. That means it is all taken over a closed surface which also is a Gaussian surface and whose volume is V. Okay, so we have to understand what is vector field. As in the previous slide, we've been taking that there is a vector field F as it is shown here, and we have to understand what this vector field F denotes. So let us consider we have a field. If we consider every point of that field as a vector, then we call such a field as a vector field. As you can see this diagram here, this diagram shows different vectors of all the directions. Similarly, to make it simple, we can tell that let us consider a huge shape or a huge bucket. Then every vector, there are vectors in the bucket. And if there are a lot of vectors, every vector having a different vector field in a bucket, then it is called as a vector field. I'll read it again. Let us consider we have a field. If we can consider every point on that field as a vector, then we call such field as a vector field. That means every point on that bucket is a vector. Then this whole bucket becomes a vector field. For example, let us take this cube. There are a lot of vectors in this cube, okay? And all these vectors have different directions, and all these vectors together make a vector field. Moving on to the next. So next we have, as we are doing Gauss divergence theorem, it is very important for us to understand what is divergence. So what do we actually mean by divergence? Let us look into this. As the theorem states, Gauss divergence theorem, it is important to understand that what divergence actually is. An easy definition of divergence is the net outward flux is called as divergence. So what do we mean by the net outward flux? Let me give an example with this Rubik's cube only. Let us assume that there is one the flux which is coming like this, and the outward is of many. Okay, for example, you're getting one, and many fields are coming outside. That means it's a positive divergence. That is, it is greater than one. If we send one field and many fields are coming outside, that is, the divergence is greater than zero, and that becomes a positive divergence. So, jumping on to what is negative divergence. For example, we send two or three fields and only one field come out of these the net field, then it becomes a negative divergence. So what is zero divergence? Zero divergence is basically the number of fields you send, the number of field lines it comes out. If I've sent two field lines here, the two field lines comes out of this. This becomes the zero divergence. As we read again, it is as a definition of divergence. This is the net outwards flux is called as divergence. Moving on to the next. Okay, so Gauss divergence theorem. In a simple way, let us understand what Gauss divergence theorem states. The flux of vector field A over any closed surface S is equal to the volume integral of the divergence. So what does this state? That there is a vector field A and there is a closed surface. This is a Gaussian surface which is closed. That is S is equal to the volume of integral of divergence. Then if we take the integral of divergence, then that will be equal to the vector field of the closed surface S of the vector field over the volume enclosed by the surface. This we can see here, right? A dot ds. This shows the flux. That is equal. Flux we can also equate to the divergence of the Gauss divergence. Okay. Jumping on to the last section, that is application of Gauss divergence theorem. So, where do we find the application of Gauss divergence theorem? One of its application is the electric field due to the infinite plane sheet on charge. What happens in this is let us consider an infinite thin sheet which is highly malleable and beaten to very thin sheet which consists positive charge and have uniform positive charge density sigma on both sides. So what do we mean by this statement? I said recently now is that we take a sheet which has a plane sheet which has positive charge on it. Okay, the throughout the sheet it has positive charge, and even the backside of the sheet it has positive charge. That is it, which means that the whole sheet is highly dense with positive charge, that is sigma on both the sides. Next, due to the symmetry of this sheet, the electric field is perpendicular to the plane sheet of the charge and it is directed outwards. So what do we mean by this? Let us assume that this is the electric sheet. Okay, and this is totally positively charged density even from top and even from bottom. The charges are positive, and this states that due to the symmetry of this sheet, the electric field is perpendicular to the plane. If this is the plane, this is the sheet, then the electric fields come out the perpendicular way, like this. The electric fields come out the perpendicular way from inside. uh, Let us take like this, the electric field cut toward inside and it comes like this. This is the way electric fields enter. That is what I have read. Due to the symmetry of this sheet, the electric field is perpendicular to the plane sheet of charges and it is directed outwards. Okay, for finding the electric field due to the plane sheet of charge at any point P, let us consider point P at this. Let this point where I have cut the point, this point, if you can guys can see, uh, let this point be P. Okay, let any point be P. Distance from R is considered a cylindrical of this section with the cross section area A as the Gaussian surface passing through the point P. So this is what happens. Um, Okay, let us assume that this is a cylindrical surface and this is the point P and it goes on the I've told you in the previous slide that electric fields move perpendicular. So this becomes a Gaussian surface and this is the electric field P at the surface area A passing through the. You can see the figure there. The P is the point and this R is the radius and A becomes the surface area of the Gaussian surface at P. Here, the electric field lines of force are passing parallel to the curved surface of cylinder. That means, as I've told in the previous slides also, the electric field lines will pass at the perpendicular to the field. And we've played this cylindrical surface. Let us consider this pen as a cylindrical surface. And we have considered this plane cylindrical surface as in the perpendicular direction. And we also know that the field lines pass in a perpendicular direction. So basically, we can say that this cylindrical surface is placed parallel to the curve and cylinder. Hence, the electric flux due to the electric field due the plane of the charge pass only through the two circular caps of the cylinder. Let Q be the charge enclosed on the Gaussian surface. So Q is the charges, and the simple conclusion is that the amount of charges Q, which is perpendicularly placed to the Gaussian surface, act perpendicular to the surface and move upwards. This is the conclusion of this practical of the Gauss diversion principle. So it is simple that the Gaussian surface is this, and and the charges move perpendicular to it. So if we put a Gauss in any surface, let for example the cylindrical surface perpendicular to it, we can see the charges Q moving in a perpendicular direction upwards. That's it for the this presentation in today's video. We will also will be discussing the Gauss divergence theorem, the derivation and the whole theorem in the next video. Because if the this discussion will be taken place in this video, it will increase the length of the video and the time limit. The increasing of time limit is strictly not permitted for us in this videos. So stay tuned for the next video where we will be discussing the derivation of Gauss divergence theorem. Until next time, keep exploring physics and keep exploring more and more topics in physics. See you in the next video. Sayonara. Thank you.